Okay, so let's begin with our new chapter of capacitor. So before that, we need to know what is actually a capacitor. So from the previous chapter, we actually did discuss about uniformly charged plates. So let's say I have two parallel plates. So these two parallel plates each contain different charges, which is positive and negative. So we did discuss about the flow of electric field strength between these two plates, which is from the positive to negative. So this one is actually my electric field strength, which is E. Okay, so the capacitor is actually designed in this form. So this uniformly charged plate is what we call capacitor. So capacitor basically is two parallel plates of each area A. So each plate has the same surface area, which is A. So separated by a distance D. So between these two plates, the distance is actually D. Okay, so this is capacitor. So what is the function of capacitor? So our function for the capacitor is actually to store the electrical energy, electrical charges, or electrical energy. So this is the function for the capacitor. So capacitor usually the symbol for the capacitor, so let me just use another color. So the symbol for the capacitor is actually in this form. So this two straight pieces is actually indicates the two parallel plates of the capacitor. So if as for the capacitor in real life, the electric component, which is the capacitor, is actually in this form. So I estimatedly draw it. So this one should be a cylindrical shape, and this cylindrical shape contains two legs. So these two legs is actually shows the positive plates and negative plates. So this is these two legs indicates the both positive plates and negative plates. So if we simplify it in two dimensions, so this is the symbol for capacitor. Okay, so let's just move on to the next parts. Okay, so let me erase this one. Alright, so let's just move on to the next part. So let me see what else. Alright, so let's just proceed to the properties of the capacitor. Properties of a charged capacitor. So this charged capacitor, so let me just highlight it. So this charged capacitor is actually meant by the capacitor, which is uh, attached to the power supply. Attached to the power supply. So there is actually two types of the capacitor, which uh, for the first condition, the charge capacitor, as we mentioned just now, which is actually attached to the power supply. As for the second condition, so the capacitor is actually what we call isolated capacitor. So this is another form of capacitor. So this isolated capacitor is actually do not attach to the power supply. So does not attach to the power supply. Okay, does not attach. So isolated capacitor is actually meant by the capacitor which does not attach to the power supply. So this is the um, two main description for the capacitor. So we need to determine it clearly, so that we need to know whether the condition of capacitor which is either attached to the power supply or not. So in this case, we're going to discuss about the properties of the charge capacitor. So the charge capacitor basically is attached to the power supply. Alright, so let me just erase this one. Okay, so since the capacitor is attached to the power supply, so this is the symbol of the capacitor. So when it is attached to the power supply, so there's a wire which attached between the battery and the capacitor. Okay, so when it is attached to the power supply, so there's the difference between the two plates. So one of the plates will be positive charge. As for another plate, basically is negative charge. So when there's a difference between the two plates of different in the form of different type of charge, in terms of different type of charge, so the positive plates, we said that the positive plate has the higher potential. As for the negative plates, so the negative plates will have the lower potential. So we know that from the electrostatic chapter, we actually talk about the electric potential is always flow from the higher potential to lower potential. So basically, the electric field strength, so okay, let me just use another color. So the electric field strength is actually flows from the positive plate to negative plates. So since there is electric field strength between these two plates, and hence it actually shows that there is actually a potential difference. So the potential difference and the electric field strength is actually relevant to each other. So if there is potential difference between these two plates, so eventually there is a electric field strength. Okay, so let me see. Okay, so we have done for this part. So I repeat again. So the electric potential, we know that it will basically flows from the higher potential region to lower potential region, which is the from the positive plates to negative plates. So since there's a potential difference and there's a distance, there is a significant distance which is d. So based on the previous knowledge we learned from the electrostatics, we know that the electric field strength is actually equals to the negative dV over dr, which is the change in the electric potential at the certain distance. So the existence of potential difference will eventually give us the electric field strength. So this is the explanation. Okay, so we're done for these properties. So this is actually the main properties for the capacitor, which is used to describe the function of the capacitor. Alright, so let me just erase this one. Alright, so let's move towards the relationship between the charge, which is Q, and the electric potential of a capacitor. So we know that, so for a charged capacitor, so this is positive Q and this is negative Q. So the electric field strength flows from positive to negative. So if we have the higher charges of the positive plates, so the potential difference produced between the two plates is actually will goes higher. So this explains that our electrical charges is actually directly proportional to our potential difference. So the larger the electrical charges, the higher the potential difference across the two plates. So basically, in this relation, we can convert it into the equation. So after changing into the equation, what we need to do is actually um, adding a constant. So this is C and this is V. So this V we actually indicates the potential difference. So it's not necessary for us to write down the delta. So the final formula what we get is actually Q is equal to CV. So C is actually equals to Q over V. So what is actually C means? So C is actually meant by the capacitance of the capacitor. So the capacitance of the capacitor is actually meant by the ability of the capacitor to store the electrical charges. Electrical charges. So the capacitance of the capacitor is actually the ability of the capacitor to store the electrical charges. So this is actually the capacitance, the explanation for the capacitance of the capacitor. So this one is actually not the true definition for the capacitance. So the true definition for the capacitance is actually So the definition is actually defined as, so this one should be the meaning for the Okay. The definition for the capacitance. So defined as the ratio. Okay, let me just erase this one. The ratio of the electrical charges to the potential difference across the two plates. Okay. So I repeat again. So the capacitance is actually the ability for the capacitor to store the um, one column of charge. So this to be more specific, ability to ability to store um, one column of charge, one column of charge per unit voltage So okay, so the ability to store one column of charge per unit voltage. So this is the explanation, or should I say the elaboration for the capacitance. So the true definition is actually the ratio of the electrical charges to the potential difference across the two plates. So this is the definition for the capacitor. Alright, so let's just move on to another part. Okay, we have done for this part, which is the definition for the capacitance. Okay, so let me just erase this one as well. Alright, so let me just observe for a while. Okay, so just now we actually talked about the uniformly charged plates. So what about the capacitance? So just now we talked about the capacitance for a uniformly charged plates. So what about now we discuss about the capacitance of a charged metal sphere? Of a charged metal sphere. Yes. Okay. So the capacitance of a charged metal sphere is actually begins with let me think how should I inscribe this. Okay, so we know that the electric potential for a charged metal sphere is actually kq over r. So q, or you can write it in terms of capital letter, depends on you. So this is 4 pi epsilon naught r. So consider this is our metal sphere. So the permittivity of this metal sphere is actually the permittivity of free space. So we consider this one is the permittivity of free space. Okay, so this one should be the metal sphere. Alright, so Q, so I write it in terms of capital letter. So if I move this V to the side of Q, so what I get is actually Q over V equals to 4 pi epsilon naught R. So since Q over V, which is the ratio of the electrical charges to the potential difference, so this is actually the formula for capacitance. So hence the capacitance is actually equals to 4 pi epsilon naught R. So this is actually the capacitance for the metal sphere. Alright, so we've done for this one. Okay, so let's proceed to the next subtopic. So this topics we're going to explain about the formula for the capacitance. So this is actually in the form of parallel plate capacitor. So this formula is actually describing the parallel plates capacitor instead of the metal sphere. Okay, so capacitor. So this will be our diagram here. So this diagram is same as the diagram we described just now. So this is actually the positive plates, which consists of positive charge, and this one should be the negative charge. So eventually the electric field strength will move from the positive plate to negative plates. So this is E, and we know that, okay, and we know that this is the plate separation, which is D. Okay, so both plates has its own surface area which is equal, so we denote this one as A, and this one is A as well. And since there is a electric field strength, so it proves that there is actually a potential difference across the two plates. Alright, so what we need to do is actually prove that C is actually equals to epsilon naught, which is permittivity of free space, multiplied by the cross surface area of the plates, which is A, divided by D. Alright, so for the first information, we know that from the previous chapter we actually said that E is actually equals to the negative dV dr. So this negative is actually used to cancel out the negative which from the differentiation of the electric potential. So okay, so after in this case we are not going to differentiate this formula again. So since this one is a parallel plate instead of the metal sphere, so in this case the electric field strength is actually equals to the change in not change in, should be equals to the potential difference divided by the plates of separation. So there is no negative, so this one need to remember that this one we actually describing the parallel plates capacitor instead of metal sphere. Okay, so our E is actually equals to the potential difference divided by D. Okay, let me just erase this one. So as for the another formula, so from the previous chapter we actually described about the electric field strength for a uniformly charged uniformly charged plates. So the uniformly charged plates, what we get for the electric field strength is actually equals to the sigma over epsilon naught. This is after some derivation. Okay, so this one is 1 and this one shall be 2. And we know that this sigma is actually equals to the charge density on the surface of each plate. So let me just write again. So this one should be the charge density on the surface of each plate. On the surface of each plate. Okay, so this one is okay. So sigma, we know that sigma is actually equals to the Q over the surface area. So this is Q over A, and this is epsilon naught, and this one is our second information still. So equating the both formula, so 1 is actually equals to 2. So this is potential difference divided by the plates of separation equals to the Q over A epsilon naught. So what we need to do is actually derive this formula. So in this case, what we have here is actually if we move this potential difference to the other side, so what we get is actually Q over V. So I told you that the delta is actually not necessary to be written. So after that, so these two variables move to the other sides again. So what I get is actually epsilon naught A over D. So Q over V is actually C. So what I get is actually C is equals to epsilon naught A over D. So this is the another important formula for the capacitance of the capacitor, for the parallel plates capacitor. Okay, instead of the metal sphere conductor. Okay, so let's move on to another part. Okay, so let me just erase all this one. Alright, so let me erase this one as well. Okay, so let's discuss about what is the factor that is actually affect the air field capacitor. So let's say this is our capacitor. So between these two plates, which is positive and negative. So between these two plates, there is actually the free space. We know that since there's a plate separation, so this region is actually the free space. Okay, so from the formula, which is epsilon naught A over D. So what is actually affecting the capacitance of the capacitor? So the answer is actually came from this formula. So what we have here is actually the capacitance is actually equals to the epsilon naught A over D. So since this epsilon naught is the permittivity of free space, and hence this one is actually a constant. So what is actually changing is actually this one, and this one. So there are two variables actually will affect the capacitance of the capacitor. So for the first one, which is the surface area, so we can see that our capacitance of the capacitor is actually directly proportional to the surface area of each plate. So if the surface area get bigger, and hence the capacitance, which is the ability for the capacitor to store one column of charge per unit voltage. So the higher the surface area of the charge plate, the higher the capacitance of the capacitor. So this is the first one. As for the second factor, so we can see that from the formula, the C is actually inversely proportional to the plate separation. So if the plate separation get larger or get longer, whatever, so the longer the plate separation, and hence the lower the capacitance of the capacitor. Okay, so this is the two main factor that will affect the capacitance of the capacitor. Alright, so let's just move on to the new subtopics. Okay, so we have done for the property of the capacitor. Okay, we've done for the property, and we have done for the formula for the capacitance of the capacitor. Alright, so let's just move on to our new subtopics. So in this topics, we are going to talk about the dielectrics. Okay, let me just use the black color. Dielectric. So assume I have a capacitor, which is the two plates. So just now what we have is actually the free space in this the free space which lies between these two plates. So what about if I insert something inside these two plates? So this something is actually what we call dielectric. So dielectric is actually inserted into the space which lie between these two plates. So before that, what we need to know what is actually the dielectrics. So the dielectric is actually the insulating materials which is inserted between the two plates. The two plates. So the dielectric is actually the insulating material which used to uh, insert or fill the space between the two plates. Okay, so different type of material has different dielectric constant. Okay, so the formula for our dielectric constant of different type of materials, different type of materials. So this we denote this one as epsilon r. So my epsilon r is actually equals to the permittivity of medium, permittivity of medium divided by permittivity of free space. Free space. So I repeat again. So this epsilon r is actually the dielectric constant. So dielectric constant is actually equals to the permittivity of medium divided by permittivity of free space. Okay, so in simplified form, so what I get is actually the epsilon r equals to epsilon divided by epsilon naught. So if I wish to find out the permittivity of medium, so hence the permittivity of medium is actually equals to the dielectric constant multiplied by permittivity of free space. So if the capacitor consists of the free space which is lie between the two plates, and hence what I get is actually the E is actually permittivity of medium is actually equals to the epsilon naught, which is permittivity of free space. So the dielectric constant for the permittivity of free space, which is epsilon r, is actually equals to 1. So that is why we said that the permittivity of medium for the free space is actually epsilon naught, which is permittivity of free space. Okay, so alright, so we have done for the property for and the formula for the dielectric. So we're going to discuss about what is actually the function for the dielectrics. So the function of the dielectric is actually used to function of dielectric. So dielectric is actually used to increase the capacitance of the capacitor. Increase the capacitance of the capacitor. Of the capacitor. So this is the function of the dielectrics. So which is help to increase the capacitance of the capacitor, which is store the one column of electrical charges per unit voltage. Okay, so how does the dielectric helps to increase the capacitance of the capacitor? So let's watch out for the mechanism for the dielectric. Okay, so before that, allow me to describe in terms of the diagram. Alright, okay, let me just erase this one first. So assume I have a capacitor. Okay, let me just draw it more accurate. Draw it properly. So this one is my plates, and this one is my second plates. So this is positive and this is negative. So in between these two plates, the dielectric is actually inserted. So this is dielectric, which is inserted into this space. So okay, let me just erase this dielectric. So we know that the dielectric is actually made out of millions of atoms or the molecules. So this assume this one is the molecules for the dielectric. So this is actually one of the roles of the dielectric. So in this case, we are going to describe the capacitor for the capacitor, which is the charge capacitor. And this charge capacitor is actually attached to the power supply. So when charge moving from this side to this side, which is positive to negative, and hence, okay, so the dielectric molecule, and this one is the dielectric molecule, dielectric molecule. So the dielectric molecule is actually get polarized. So this one should be positive, negative, positive, negative, positive, negative, positive, negative, positive, and negative. So we can see that the molecule is actually there is a charge exerted on molecule. So when the charge exerted on molecule, and we can say that the molecule is actually polarized. Molecules are polarized. So the polarized molecule will align themselves between the two plates. Align themselves between the two plates. So after aligning themselves between the two plates along, or we can say along the two plates, so after being polarized, so this polarized molecule, which is aligned along the two plates, will produce an electric field which is opposed the direction of the normal electric field. So this is actually we can say that is actually the reverse electric field. So this one is a reverse electric field. So I repeat again, when the charge is supplied to the capacitor, which is consists of dielectric inside it, so the molecule of the dielectric will eventually get polarized. So this is the first statement. As for the second statement, so the polarized molecule will eventually align themselves along the two plates. So align themselves, which is actually forming a straight line along the two plates. So the polarized molecule after that will eventually produce a reverse electric field. So this is the reverse electric field which opposing the normal electric field. So this one, assuming this one should be our normal electric field. So this is E and ER is the reverse electric field. So after that, after the reverse electric field is produced, so my E, which is the electric field, so the electric field will eventually decrease, which the electric field is cancelled by the reverse electric field. So the resultant electric field, which is the resultant electric field, which is the change in electric field, is equals to the E minus the reverse electric field. So this change in E is actually smaller than the initial electric field. Okay, so I should not use this one as the symbol. So I repeat again. So this change in E, which is the resultant electric field, is actually lower than the initial electric field due to the initial electric field is cancelled by the reverse electric field. So after the electric field being cancelled, so we know that my electric field strength is actually equals to the change in potential difference divided by the plates of separation. So in this case, my electric field strength decreased and hence the potential difference across the two plates will also decrease. So the potential difference across the two plates decrease and hence we know that C is actually capacitance of the capacitor is actually the ratio of the electrical charges divided by potential difference. So my potential difference, electric potential difference decreases, and in this case, okay, so never mind. So since my electric potential difference decreases, and hence this will eventually provide us the increase in the capacitance of the capacitor. Okay, so alright, so I think there's some mistakes here, and this one should be an isolated charge, not a charge capacitor. So this one is my mistake, sorry. So this one, I repeat again, this one should be the isolated charges, and this one is the isolated charges. So this experiment is actually performed in the isolated capacitor. So the charge is being isolated, which is the capacitor is not attached to the power supply. So this one is the isolated capacitor. Alright, so in this case, back to this formula. So in this case, my electrical charges is actually constant. So this is the constant. So my Q is constant, and hence the variables that is actually changing is actually the capacitance and the potential difference. So decrease in the potential difference due to the decrease in the due to the decrease in electric field strength will provide us the increase in the capacitance of the capacitor. Alright, so this is the mechanism. So let us just describe in form of sentence. So in the form of the sentence, so for the first one, when a dielectric is inserted into a charged and isolated capacitor, so this one is actually an isolated capacitor, the dielectric molecules will be polarized and aligned align themselves along along the two plates to produce. So this is actually an important note, and sorry, not an, to produce a reverse electric field. So this one should be ER. Okay, so the electric field, so the reverse electric field will the reverse electric field so this one we should write it in terms of electric field strength, which is more accurate. The reverse electric field strength will decrease the electric field strength across the two plates. So decrease in electric field strength decreases the electric potential across. Okay, there's no more spaces, so let me just write it here. So here we have the across the two plates, decrease the electric potential across the two plates, hence the capacitance of the capacitor increases. So this is actually the mechanism for the dielectric, which inserted into the spaces between the two plates of the capacitor. Alright, so I think we'll stop here now, and we will discuss this chapter in the next coming video. So I'll see you next time. Thank you. Bye.